In this video, we're going to look at the definition of a function. And in particular, we're going to look at the relationship between two sets of values or two variables that in fact defines a function. So not all relationships between variables are in fact functions. Let's have a look at the first point. A function is a relationship between two sets where each value in one set, and we'll call that the independent set, associates with at most one value from the other set. So we'll call that the dependent set. So the dependent set depends on the independent set. So in terms of variables, the independent set's normally the x variable, the dependent variable is normally the y variable. It doesn't have to be those two particular ones, but just for the purposes of this explanation, I'm just going to sort of keep it nice and simple. So let's have a look at this example here. So what I've done is I've sort of drawn a diagram here with two sets of values. Values doesn't necessarily imply they're numbers or numerical values. They can be anything, any data. So the independent set, so X, contains some letters of the alphabet, so A, B, C, D. The dependent set, Y, contains values, and the arrows basically show a mapping between the values in the independent set to the values in the dependent set. So let's have a look here. A in the independent set associates with the number 2 in the dependent set. B associates with 3 and D associates with 4. Now this is an example of a function because every value, or at least every value in the independent set associates with no more than one value in the dependent set. Okay, so A associates with 2, B associates with 3, C doesn't associate with anything, and that doesn't matter as long as it's no more than one value in the dependent set. So this is what we call an example, or it's an example of a one-to-one function. In other words, one value in X associates with no more than one value in Y. Let's have a look at another example. So just this diagram here up the top there. So again, we have the independent set, and that's usually on the left-hand side. The dependent set's on the right, and the arrows obviously go from left to right. Now, this is also a function. Now, you might notice that B associates with 2, and C also associates with 2. That doesn't break the definition of a function because every value in X associates with no more than one value in Y. And the values don't have to be distinct either. They can be the same value. So A associates with 1, B associates with 2, C associates with 2. As long as a value in the independent set, so the value in X, doesn't have multiple arrows coming off the letters. Okay, so you can see here, in fact, if I hid that part there, okay, you can see that there's in fact only one arrow coming off the letters, off each of the letters in X. So this is also a function, and we call it a many-to-one because it's possible to have many X values associating with, say, one Y value, and that's okay. That's still a function. Now let's have a look at an example of a relationship that breaks the definition of a function or that is not a function. So have a look at this one, and hopefully you can see, in fact, all you need is one example or one association that breaks the rule, and therefore the entire relationship is no longer a function. You just need one mapping or one example which breaks this rule. Okay, A associates with 1, B associates with 2, so far so good. C doesn't associate with anything, and that's okay. It still doesn't make it a sort of a non-function. It's still a function at this point. But look at D. D associates with 3, but also associates with 4 as well. It's kind of like, a flick a switch and two different things happen. You can, two different outcomes occur simultaneously from just the one the one input or the one value in X. That is not a function. So because we have multiple arrows coming off one of the X values pointing to two different Y values, or could be more than two different Y values, this is not a function. And this is what we call a one-to-many relationship. Okay, this is also called a relation. So what do you call a relationship that's not a function? We just call it a relation because it is a relation. Sure, x is related to y or y is related to x. There is a relationship between those two, but doesn't follow the definition of a function, which means one x value can associate with one y value, at most one y value. Okay, so this one breaks the definition. Let's have a look at another type of example, and this one is one that looks at a variety of points, and we're asked to determine if these points in fact represent a function. So we have the point 1, 2, 2, 4, 3, 5, and 1, 1. So you might want to have a quick think about it, have a look at those points. If you want to pause the video, you're welcome to do so. Do these 4 points in fact form a function or represent a function? So these are the x values, these are our y values. So x, y, so on and so on. You can probably see that this is not going to form a function because we have an x value here that maps to 2. In fact, I might just, so these are our x values. Okay, we have 2 maps to 4, 3 maps to 5, so they're okay. But this 1 sort of is repeated. So this x value of 1 is also here, x value of 1 there. 1 maps to 2, but this 1 maps to 1. And there's the y values. So one x value cannot map to more than one y value. So this is clearly not a function. Okay, so it's a relation. Okay. Sorry, it's not the neatest there, but trying to squeeze it in the end there. All right. Now let's have a look at some algebra. Well, algebra, sort of an example of two functions, or two equations, should I say, where one is a function and one is not, and have a think about why, in fact, this is the case. So for any equation to be a function, every possible x value, and we haven't spoken about sort of domain and range yet, I'll leave that for another video. But every possible x value, or every permissible x value can be associated with at most one y value. Again, by the definition of a function. So an example, y equals x squared. That would be a function. Now that's a parabola, okay, so we know what that looks like, so it sort of looks like that. Any particular x value, when you square it, you're only going to get one possible y value that results. And again, the y values don't have to be distinct. So let's say, for example, x equals -3. How many y values result from that? Well, if you square -3, the y value that maps to that is the y value of 9. Okay, so it's not like there's two possible y values for this one x value. However, there is another x value that would also give you a y value of 9. So if x equals +3, we square that, you get 9 as well. But that's okay. You can have one x value mapping to one y value, and the two y values can in fact be the same y value. So you can have multiple x values giving you the same y value. That's okay. That's still a function. But what about if I square the y instead of the x? So y squared equals x, and sort of a somewhat unrelated question. If you were to graph that, I wonder what you'd get. You can have a play with that and see what happens. In fact, when we do inverse functions, we'll look at this. But y squared equals x is not a function. Now, have a think about why that is in fact the case. All you need is one example or one instance where it breaks the rule, where one x value associates with multiple y values. The whole thing is no longer a function. So let's say, for example, x equals 9. What values can y take such that y squared equals 9? Sort of moving on there. So if we let x equal 9, that's our independent variable. Y squared equals 9. We can see here that we have two cases, don't we? We can have y is equal to -3, because -3 all squared gives you 9. So that's so that can work. Y though can also equal 3. So we have two y values that associates with the one x value. So it's a relationship that looks like this. This is x equals 9 associates with -3 and +3. So you have one x value associating with two different y values. That breaks the rule. It is not a function. This is just a relation. Thanks for watching.